In this video, I will be discussing the process of writing balanced half equations and overall equations for redox reactions under acidic conditions. Now, what acidic conditions means is that first of all, you're going to have water present, so the reaction will occur in a solution. And second of all, you're going to have H plus ion present because it is an acidic condition. So an example of a natural acidic condition that you will see in nature that cause or facilitate or speed up a lot of redox reaction is rainwater. Rain is slightly acidic, so it actually creates an acidic condition for, say, wet rusting of metals to occur. But that's not the only acidic condition that you can get. Just a quick recap, a redox reaction is a reaction that involves a transfer of electrons. So there are two processes, reduction, which is the gain of electrons, and oxidation, which is the loss of electrons. So there is an acronym that you can use to remember this, which is OIL-REG. Oxidation is loss of electrons, and reduction is gain of electron. So this is the first acronym that I think it's probably good to start committing to your memory. Now, normally in a redox reaction, we would represent these two processes separately using what is called a half equation. So every redox reaction will have two half equations, one for reduction and one for oxidation. So what I'm going to explain in this video is how you can write the two half equations, and then I'm going to show you how you can add the two half equations together to get the overall equation for the reaction. Now, if the reaction is under acidic conditions, then you can use this procedure called KOHES, to write and balance the half equation. So generally there is a step 0, and the step 0 is for you to work out what the reactant and the conjugate product is using oxidation numbers, and I show you how to do that. And then you have the actual 5 steps of KOHES. Or KOHES. So K means key element. So the first thing that you want to balance is your key element. This is essentially the element that has a change in oxidation number. That has a change in oxidation number. So your key element is the element that actually undergoes either reduction or oxidation in oxidation number. Okay. And then once you have balanced the key element, you're going to balance oxygen by adding H2O. This is because the reaction is under acidic condition with H2O present, so you are allowed to add water into the equation. Once you have balanced oxygen, you're going to balance hydrogen by adding hydrogen ions. This is a significant part of an acidic condition. If the condition is not acidic, you are not allowed to add H plus ions to balance the hydrogen. We're not going to talk about non-acidic condition this year, but later on I will explain what happened when the condition is basic and then some other conditions. And then once you've balanced the key element oxygen and hydrogen, you're going to balance the charge by adding electrons. You can only balance the charge by adding electrons. You cannot add any more protons or anything else. This is a redox reaction, so electrons can be used. And S stands for state, so don't forget state at the very end. Okay, so KOHES. All right, I'm going to show you two examples of how KOHES actually work. So this is example A. Write the half equations for the following processes under acidic conditions. So the first one is a reduction of MnO2 to Mn2+. So I already give you the conjugate pair here, so you don't necessarily need to use step 0, but you can if you want to. So MnO2 is oxidation number of manganese +4, and then it goes to +2. So this is a reduction, which means that there is a gain of electrons. So if electrons is gained, what you should see is that you're going to see electrons in the reactant side because you're gaining it. So it has to be added to the reactant. So electrons will be in the reactant side. All right. So I basically already have my conjugate pair, so I don't really need step 0. I'll show you when you need to use step 0 a little bit later. So the first thing I'm going to do is I'm just going to write the reactant and the product. My advice is to leave a lot of space in between the reactant and the arrow, and then the product and the end, so you can add stuff as you go along. Okay, we're going to go through the 5 steps. So step 1 is to balance the key element. The key element in this case is going to be manganese. It goes from +4 to +2, so it's the substance that undergoes reduction here. However, the key element is already balanced. I have 1 manganese on the reactant side and 1 manganese on the product side, so I don't have to do anything. So key element's balanced. Step 2 is to balance oxygen by adding H2O. Now you have 2 oxygen on the reactant side here. So what I need to do is to add 2 water on the product side so that my oxygen is balanced. So by adding 2 H2O, I will have 2 oxygen on the product side as well, and my equation is balanced for oxygen. So that's step 2. Step 3 is to balance hydrogen by adding hydrogen ions. So because I've just added 2 H2O onto the product side now have 4 hydrogen atoms. So I need to add 4 H plus onto the reactant side so that the hydrogen is balanced. So now you have 4 hydrogen on the reactant side and 4 hydrogen on the product side. Okay, this is where it gets a little bit tricky for some people. You need to balance the charge by adding electrons. So you want to think about the overall charge of the reactant side and the overall charge of the product side. The one thing to keep in mind is that you have to consider the coefficient when you calculate the charge. So if you look at the first substance, which is MnO2, the charge of MnO2 is 0. If you look at the second substance on the reactant side, you have H+, so the charge of each hydrogen ion is 1+, and you have 4 of it, so the charge here is 4+. So the overall charge on the reactant side at the moment is 4 positive, or 4+. Now if I look at the product side, each manganese is 2+. There's only 1 manganese, so I don't have to double this charge or anything. And each water has a charge of 0. So if you have 2 water, it's still 0. So the overall charge on the product side is 2+. The one thing I want to really emphasize is you only need the charge on the reactant and the product to be equal to each other. You do not need to bring it down to 0. They just need to be equal to each other. So if I want the reactant side and the product side to have the same charge, what I need to do is to add 2 electrons onto the reactant side. Because if I add 2 electrons, the reactant side will have a charge of 2+, because 4 minus 2 is 2. So I'm going to balance the charge by adding 2 electrons on the reactant side. And this matches my prediction earlier that this reaction is reduction and you should see electrons on the reactant side. If for some reason you have to add electrons on the product side, it is an indication that you've done something wrong in the previous steps. Okay, and then finally we're going to add states. I'm not going to be too hard on you for states at the moment because you probably don't know what MnO2 is. But you should know the general rule of thumb is that ions will be aqueous, H2O is liquid, and electrons have no state. It has a charge, no state. Okay, so if you're not sure what MnO2 is, it's fine, but you should know the state of every ion as well as water. Okay, so this is the final question answer. MnO2 plus 4H plus and 2 electrons going to MnO2 plus and 2 water. All right, let's do another example. We have many examples today. So the second example is an oxidation of SO2 to SO4 2-. So I'm just going to quickly find the oxidation number just so I can confirm that this is indeed an oxidation. And you can see that sulfur has gone from +4 to +6. So it is definitely oxidation. There is an increase in oxidation number. And with oxidation, electrons is lost. So if electrons is lost from the reactant, you're going to see electrons in the product side. So if later on when we look at our final answer, we don't have electron on the product side, we have done something wrong and we have to go back and check. There are multiple ways to check this, but this is just one of them. All right, I'm going to start again by setting up the reactants and the product. So SO2 going to SO4 2-, and I'm going to follow KOHES again. So let's start with balancing the key element. The key element in this case is going to be sulfur. Sulfur is a substance that has a change in oxidation number. And if you look at the reaction we have so far, there is one sulfur on the reactant side and one sulfur on the product side. So sulfur is already balanced. I don't have to do anything with sulfur. Next step is to balance oxygen by adding H2O. There's 4 oxygen on the product side and only 2 on the reactant side. So I need to add 2 H2O so that the oxygen is balanced. Only the oxygen. So now the oxygen is balanced. The next step is to balance the hydrogen by adding H+. So there are 4 hydrogen on the reactant side here. So I need to add 4 H+ onto the product side so that hydrogen is balanced. And then we arrive at the charge step, which normally is the most difficult step. So just take your time and then you get faster with practice. So SO2 has an oxidation number, probably just stick to blue. SO2 has an oxidation number of 0. Sorry, not oxidation number. SO2 has a charge of 0. H2O has a charge of 0. So the overall charge on the reactant side at the moment is 0. If you look at the product side, SO4 2 minus has a charge of 2 minus, and you only have one of it, so it's just 2 minus. And you would have a charge of 4 plus from the 4 hydrogen ions. So the overall charge on the product side is 2 plus. So reactant side is 0, product side is 2 plus. I need them to be equal to each other, and the only way to do that is to add 2 electrons onto the product side, because electrons is negative, so 2 minus 2 will equal to 0. So I'm going to add 2 electrons here, and once again this matches my prediction earlier that this is oxidation, and you should see electrons on the product side as it is lost. So charge is balanced. Finally, I'm going to add states in. SO2 is a gas. You may not know it, that's fine, but just make sure you know that water is liquid and all the ions will be aqueous. Okay, so that's the second example. So just follow the step, and with practice, you get faster. All right, let's go through a few more examples, especially when you need to use step 0. So this is a second example, which is cellular respiration. Cellular respiration is a redox reaction, and this is a following overall equation for cellular respiration. Even though I think this should be AQ, to be fair. Okay. Now, this is a second type of question when I give you an overall redox reaction and I ask you to write the 2 half equations under acidic condition. Obviously, cellular respiration is acidic condition. It definitely has water, and the bio people will tell you that there's some proton carrier, so there's definitely hydrogen ions present. So this is where step 0 comes in. Because I need to write the 2 half equations, I need to write reduction and oxidation. So the first thing I need to do is to actually figure out the oxidizing agent and the reducing agent, so I can work out which substance will undergo reduction, which will undergo oxidation. When in doubt, always by oxidation number. So -2 for each oxygen, +1 for each hydrogen. So the oxidation number of each carbon atom in glucose is 0. O2 is pure, so 0. This is -2, +4, and -2, +1. Okay, so I'm going to try to identify the reactant and the conjugate in the product. If we look at carbon, carbon has undergone an increase in oxidation number from 0 to +4. So this is my first conjugate pair. C6H12O6. Hold on, let's just create some room here. C6H12O6 going to CO2. This is my first conjugate pair. You have carbon going from 0 to +4. This is also oxidation, which means that electrons should be on the product side once you finish your balancing. Okay, so this is the first thing. So step 0, using oxidation number, basically allows you to extract the relevant conjugate pairs from the overall equation. Now I should be able to write the other pair here. The other pair is going to be the reduction of oxygen, electron on reactant side, and the other pair is going to be O2 going to H2O. Now, some students ask, why is it that I pick this species and not the other one? Because they both have oxygen on the product side, with an oxidation number of -2. You can't pick CO2 as the conjugate of O2 because CO2 has carbon as well. So you basically cannot pick the species that also contains the reducing agent. So you have to pick the one that has H2O because hydrogen doesn't change in oxidation number. So don't pick CO2. Don't pick something that has another element with another change in oxidation number. That's not gonna, you're not gonna be able to balance the equation. So oxidation, an increase in oxidation number, carbon goes from 0 to +4, and then reduction, there is a decrease in oxidation number of 0 to -2. All right, so that's step 0. I'm going to go through KOHES again. Step 1, balance the key element. Key element in the first case is carbon. There are 6 carbon on the left and 1 on the right. So you need to balance by using coefficients. So I'm going to add a 6 in front of the CO2. So that's step 1. Step 2 is to balance oxygen by adding H2O. So I have 6 oxygen on the left and 12 oxygen on the right. 6 times 2 is 12. So you need to add 6 H2O onto the left so that you have the same amount of oxygen on either side, which is 12 in this case. And then I need to balance hydrogen by adding H plus ions. So there's 12H from here, and then there's another 12 from the water. So I have 24 hydrogen atoms in the reactant side. So I need to follow that with 24H plus on the product side so that you can balance the hydrogen. Now, if you are doing biology, hopefully you can see that this is basically the equivalent of, well, is it glycolysis? I mean, the breakdown of glucose is going to produce protons, and that protons is used for the other process. Okay. And then this is the best, well, the highlight, which is balancing the charge by adding electrons. So the charge of glucose is 0. The charge of water is 0. So the overall charge on the reactant side at the moment is 0. Now on the right side, I have 0 being the charge of CO2, and then a 24 plus from 24 hydrogen ions. So the overall charge on the right is 24 plus. So in order to balance the charge, I would need to add 24 electrons onto the product side so that this charge is brought down to 0 to equal to the reactant side. So 24 electrons. Okay, so that's my electrons, and then I'll just put states in: liquid, gas, and aqueous. Is it common knowledge that CO2 is a gas? I'm gonna say yes. So that's my oxidation half equation. You can delete like all of this and just write the final thing. Okay, let's look at the reduction. So same deal, we're gonna, oh, this one is really interesting. Well, it's not that interesting, but it's a bit shorter because the key element is actually oxygen. So oxygen has a decrease in oxidation number, so it is the key element. So I need to balance the key element. I have 2 oxygen on the left and only 1 on the right, so I just need to use the coefficient and write the coefficient as 2. So now oxygen, or the key element, is balanced. Since the key element is already oxygen, I've already done step 2 as well. I now need to balance hydrogen by adding H+. So I have 4 hydrogen on the right, so I need to add 4 H+ on the left. And the hydrogen would be balanced. For those who do biology, this is essentially electron transport chain. So the oxygen will receive the protons to make water. This is essentially the reaction at the very end there. I will now balance the charge by adding electrons. So there is a 0 charge on oxygen and 4 plus on the 4 hydrogen ions. And on the product side, the charge of water should be 0. So in order to balance the charge, you're going to need to add 4 electrons so that you bring down the charge of the reactant side to 0. So this is 4 electrons. And then you put in states. All right, oxygen is a gas, H plus is aqueous, and water is liquid. maybe just delete this is to tidy it up a bit. So this is the reduction half equation. Okay. So this is a second type of question. I give you an overall equation and you have to extract the equivalent conjugate pair to write the two half equations for me. Use oxidation numbers as a start, and then once you get the pair, just follow KOHES and you should be able to balance the equation. All right, let's do one more example for this type of question. This is hydrogen peroxide decomposition, which is the elephant toothpaste, which a lot of you have seen. Essentially, you add detergent and it forms up the oxygen gas that's produced from the reaction. But the reaction does happen even without the the detergent, and it does happen fairly slowly without the catalyst. All right. This one is very interesting because hydrogen peroxide is one of the exceptions to the oxidation number rule, in that the oxidation number of oxygen is actually -1 and not -2, and hydrogen is going to be +1. I mean, if you look at this, it has to be -1, otherwise the sum of all the oxidation numbers won't equal to 0. All right, I need to write the two half equations again. So I'm going to start by finding oxidation number. So H2O2 going to O2 and H2O. The other reason why I pick this equation, beside the fact that it is elephant toothpaste, is it is very interesting because you essentially have the same substance undergoing both oxidation and reduction, hence cell decomposition. So it can happen. You can have the same thing undergo oxidation and reduction. So it reacts with itself essentially. It's very similar to like an amphiprotic acid that can act as an acid and a base to itself. So this is like the redox version of that. All right, let's start with I don't know, oxidation maybe. So oxidation is when you have a gain of oxidation numbers and you will see electrons on product side. So if you look at the oxidation numbers that we have found, you can see that oxygen has an increase in oxidation number from -1 to 0. So the conjugate pair that I'm going to use is H2O2 going to O2. One thing that I didn't mention in the previous example is that you don't have to consider the coefficient at the start of the substance when you extract the pair from the overall equation. So I don't care that there's a 2 here, okay? I mean, if you include it, it's probably not going to make any big difference because you're going to balance it anyway, but you don't have to. So I'm just going to go H2O2 to O2 is the oxidation part, and the reduction is going to be when there is a decrease in oxidation number, which is -1 to -2 in this case. So it's H2O2 going to H2O. So you have electrons on reactant side. Okay, let's follow KOHES to balance both equations. If you want to try it yourself, feel free to pause the video and do it yourself first, and then you can check your answer later. That's probably going to be more useful. But if you still want to watch it again, like one more time, you can do that too. So I'm going to start by balancing the key element, which in this case is oxygen. It's the one that has an increase in oxidation number from -1 to 0. However, oxygen is already balanced. I have 2 oxygen on the reactant side and 2 on the product side. So key elements balanced, oxygen's balanced. Oh, this is good. All right, I'm going to balance the hydrogen by adding H+. So we're just going to add 2 H+ here to balance the 2 hydrogen atoms on the reactant side. And let's get to the state. I'm going to do this a little, the charge. I'm going to do this a little bit more quickly. So you have 0 being the charge on the reactant side, and the charge on the product side is 2+, so I need to add 2 electrons on the product side, so it agrees with my prediction earlier that this is oxidation. So now the product side has a charge of 0 as well, which is the same as the reactant. And last but not least, I'm going to add states. Just follow the state given in the question originally if you're not sure what the state of hydrogen peroxide is. But if you've seen the elephant toothpaste, hopefully you see that it's a liquid at the start. Okay, so that's my oxidation reaction. Cannot believe I was going to write like aqueous for oxygen gas just then. All right, reduction. So with reduction, we're going to do the same thing. We're going to balance the key element, which oddly enough is also oxygen. It's going from -1 to -2 in oxidation number. Now, however, oxygen is not balanced here. There are two oxygen atoms on the reactant side, and there's only one on the product side. So I need to double this so that oxygen is balanced. Key elements oxygen. So I've done step 1 and 2 in one go there. It's always good when oxygen is also the key element, like you save one step. Okay, I need to balance hydrogen by adding H+. I have 2 on the reactant side and 4 on the product side. So you just need to add 2 H+, and then your hydrogen is balanced. And now we're going to balance the charge by adding electrons. The reactant side is, well, has a charge of 2 plus at the moment, 0 from hydrogen peroxide and 2 plus from the 2 protons. And the product side has a charge of 0. So I need to add 2 electrons here so that the charge is balanced. And then just put in states. So H2O2 is still liquid. This is AQ, and that's liquid. So you can see how in this particular case, it is the opposite, reverse of the oxidation, but it doesn't have to be. Okay, so that's second example of the second type of question, which is when I give you an overall equation and then I ask for the two half equations. All right, this is example 3. Do I have, oh, I only have one of these. So this is probably the hardest type and it takes the longest time to do. This is when you basically only get information of the conjugate pairs and then you have to use that to write the two half equations and then add them together to get the overall equation. And a lot of the time it's written in words as well. So when zinc powder is sprinkled into an acidified, now the word acidify indicates that this is an acidic condition, so you can use KOHES, acidic condition. When zinc powder is basically solid zinc, powder is solid as a state. So zinc powder is sprinkled into an acidified solution. A solution is IQ. So this is K2Cr2O7 IQ. So we basically have, if we just translate what's happening, you have zinc powder and potassium dichromate IQ. A reaction occurs that leaves zinc 2 ion. Remember that the Roman number indicates the charge of the ion for transition metal. It's an ion, so the state is aqueous, so zinc 2 plus AQ, and chromium 3 ion, so Cr3 plus AQ. So Cr3 plus AQ. I think I just regretted one of my decisions then, but should I tell you why? Do you need why? Okay, I'm gonna just make it a bit easier and change this to a solution of dichromate ion, okay? Potassium is actually a spectator ion, so you're gonna have to actually change it to dichromate anyway, but I'm gonna give this to you in the question, so you don't have to worry about knowing how to change from potassium dichromate to dichromate ions. Just trust me that I will definitely give you the substance without the spectator ions. Okay, so dichromate ion is Cr2O7, 2 minus. So let's just rewrite the question. When zinc powder is sprinkled into an acidified solution of dichromate ions, just to make it a little bit easier, so you don't have to worry about the potassium, a reaction occurs that leaves zinc 2 plus ion and chromium ions. Okay. This is by no means the balanced overall equation. This is just me translating the information into symbols. In order to actually write the overall equation, I need to first write the two half equations. But this is enough so that I can work out the conjugate pairs. So the first pair is definitely going to be zinc going to zinc 2 plus, for sure. And you can tell that this is oxidation. There is an increase in oxidation number from 0 to positive 2. Or you can just see an increase in charge. So this is the oxidation, which means that the reduction must be the chromium one. So reduction is going to be Cr2O7 2 minus going to Cr3 plus. But if you're not sure, you could find the oxidation number Cr2O7 2 minus and -2 +6, I think is going to be chromium. And then it goes from +6 to +3, so it is a reduction in there is a decrease in oxidation number. Okay, we're going to balance the two half equations first. The key element is zinc. This one is probably the easiest one to balance. There's no oxygen, no hydrogen, so I can go straight from key element to charge. My key element's already balanced anyway. There's only one on each side. So I just add 2 electrons and then I put in states. Okay, that is definitely not aqueous. Solid, aqueous. Okay, so the oxidation overall, or the oxidation half equation is this. Let's do the reduction. Just so that it doesn't look too confusing, I'm going to just remove the oxidation number, okay? Alright, key element is chromium. It's the one that has a change in oxidation number. I have 2 chromium on the left, so I need 2 on the right. That's key elements. Oxygen, there's 7 oxygen atoms on the left, so I need 7 H2O to balance the oxygen on the right. Hydrogen, I have 14 on the right, so I need to add 14 on the left. And then we get to charge. Now this charge people tend to make a mistake on. So chromium dichromate ion has a charge of 2 minus, and then you have 14 plus from the 14 hydrogen ion. So the overall charge on the reactant side is 12 plus. You have 2 chromium 3 plus ions, so that's going to give you an overall charge of 6 plus. And then there's 7 water, which is 0. So the overall charge on the right is 6 plus. Now you don't need them to be the charge to equal to 0. You just need the charge to equal to each other. So in order to equal the two charge, I need to bring the left side down by adding 6 electrons. So 12 minus 6 is 6, so they will have the same charge. So this is 6 electrons. And then I add state. So aqueous, 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 and liquid. So this is the reduction half equation. All right, so we have done 2 steps. So far, we've done 2 things. The question asks for 3 things, the 2 half equations and the overall equation. You've done the 2 half equations. I'm going to show you how you can add these 2 half equations together to get the overall equation. So let's just rewrite the 2 half equation. Oxidation is zinc going to zinc 2 plus and 2 electrons. Just for the sake of saving time, I'm not going to rewrite the state for now, because this is not my final answer, this is just my draft. 14H plus and 6 electrons going to 2 Cr3 plus and 7 H2O. So these are my 2 half equations. As the name suggests, you can add them together to get the overall equation. Then you add 2 halves together to get the whole. The only thing that you need to do before you can add the 2 half equations together is you need to balance the electrons. The electrons right now are not balanced. I have 2 electrons on the product side and 6 on the reactant side. That is not good. When you add the 2 half equations together, the electrons need to cancel out. So if you have 2 on one and 6 on another, if I add them together, they're not going to cancel out. So what I need to do actually, and I may just write this underneath so you can see. So what I need to do is I need to balance the electrons between the reduction and oxidation. Hold on, let me just rewrite the reduction one. So 2 Cr3 plus and 7 H2O. So I'm going to do that by multiplying the oxidation half equation by 3. So if I multiply this by 3, I will have 3 zinc, giving me 3 zinc 2 plus and 6 electrons. So if I multiply the oxidation by 3, then I will have the same amount of electrons on oxidation and on reduction. So that's good now. So in order to add the 2 half equations together, you first need to make sure that the reduction and oxidation have the same amount of electrons. And if you don't have that, you can achieve it by just finding the lowest common multiples of the 2. In this case, is 6. I'm not going to go through what lowest common multiple is. I'm sure we know what it is already. And now I'm going to add these 2 together. Okay, so when you get better, you can do this a lot of this in your head, but I'm just going to add all the reactants together. So 3 zinc plus Cr2O7, 2 minus, plus 14H plus, and 6 electrons. So I'm just writing out all of the reactants, and then I'm going to write out all of the products. That's what it means by adding equations together. Okay, so 2Cr3 plus and 7H2O. Okay, so this is adding all of the reactants together and adding all the products together. What you then have to do is you have to simplify this equation. So if you have 6 electrons on the reactant side and 6 electrons on the product side, you can cancel them out. If there is any substance that appear on both sides of the equation, you should cancel them out. So in this case, it's only electrons, but I think in some of the other examples, you may also have hydrogen on both sides, water on both sides, so you do have to simplify them. So final answer for the overall. I'm just going to rewrite this again so it looks neater. So 3 zinc, and then state is solid, Cr2O7, 2 minus, aqueous, plus 14H plus, going to 3 zinc, plus 2 chromate ion, and 7H2O. It takes a lot of work to get to this overall equation, so whenever you finish that, pat yourself on the back for a job well done. It may seem very overwhelming, but this is a skill that you will get better very quickly with practice. So just do the practice questions and you will get better before you know it. That's all. Thank you.